All right, everybody. Welcome to the next chapter, chapter 13. We're going to start with 13.1, which is vector fields. Okay, so a vector field, ooh, that's a little big. A vector field, let me highlight that since that's what we're talking about, is a function and we're going to put a little arrow on it. And we typically write this. This means it goes from Rn into Rn. Okay? So what do I mean by that? Let's say we have, you know what? We actually could do this. They don't have to be the same dimension. So let's take, for example, f of xy. This goes from R2, and the 2 indicates that we have 2 inputs into R3. The 3 indicates that we have 3 outputs. And we're going to write it as a vector. Okay, P, Q, and R. Just sort of an idea. Notice that P, Q, and R, they follow each other in the alphabet. So let's do a typical example. Let's do an actual example and not just an abstract one. So this one is actually the electric field. The electric field has inputs in space and outputs in space. Okay, and it's often written like so. E of x equals, this is an epsilon Q over, and I'm going to write this x cubed over x hat. Okay, now x, when I don't have an arrow on it, is actually the square root of x squared plus y squared plus z squared. It's the length of the vector. Okay? All right. Now, we could write this, of course, in vector format. We haven't written it like that. But we could have epsilon q over x cubed in front as a scalar. And then x, y, and z. Okay, so this is the electric field. Okay. Similarly, gravitational field, we'll pass on that. Now, a vector field is called conservative okay, if it is the gradient of a scalar function. Okay, so let's take as an example f, well, you know what, let's call it something else. Let's call it phi here. Phi of x, y, z equals epsilon q over x. Okay? This is actually a scalar function that's going to give us the electric field. Actually, I need a negative on it. Sorry about that. Let's see how that happens. I know, it's hard. Let me instead, because this x is not the same as this x, so let me write this instead as r. Let me change that up there too. And then if I'm going to do that, I'm going to change this to be an r hat. Okay. All right. So let's go ahead and show how the electric field comes out of the scalar function. This is often called the electric potential. Okay, so, oops. Okay, well, let's start by taking the partial with respect to x of phi. It's going to have a negative sign there. Epsilon q over, now instead of r, I'm going to write square root of x squared plus y squared plus z squared equals, now this is, if you think about this, this is this thing raised to the negative 1/2, right? So we're going to get a 1/2 in front, negative, but it's going to cancel the negative with that. So we're going to get positive 1/2. So positive 1/2 times 2x epsilon q over, now it's not square root, but it's going to be to the 3/2. Now, the 2's are going to cancel. Let's do that in orange. Okay, so this becomes epsilon q. Oh, let's not do that in orange. Let's do that in blue again. Epsilon q over, now x squared plus y squared plus z squared to the 3/2. Well, that's r to the 3rd, right? So that's r to the 3rd. And then we're going to have an x. Okay. I can do the same thing. Negative partial with respect to y of epsilon q over square root of x squared plus y squared plus z squared equals, pretend I did it, epsilon q r cubed. This time we're going to get a y. Same thing when I do this in z. Negative partial with respect to z of epsilon q square root of x squared plus y squared plus z squared equals epsilon q over r cubed z. Let's put that in a vector, and we're good to go. All right, be back in the next video.